Have you ever stopped to wonder what makes AI tick? And maybe more importantly, what makes it tick fast? Well, today we're going under the hood of some of the most powerful chips on the planet, the GPUs, to figure out what it really takes to write high-performance code. And our whole journey kicks off with a pretty surprising problem.
You know, AI models, especially those huge language models we hear about all the time, are just crunching billions and billions of calculations. But here's the thing, raw processing power, it's not the whole story. There's this hidden bottleneck, this kind of traffic jam that's slowing everything down. So what's really putting the brakes on the speed of AI?
It all comes down to something called the memory bottleneck. See, the weird thing is, our ability to compute stuff has gotten way faster over the years, but the speed of memory just hasn't kept up. So most of the time, the chip is just sitting there, twiddling its thumbs, waiting for data to show up. This whole waiting game is the #1 enemy of performance.
Now, here's a really great way to think about this. Imagine the GPU's main processor is a light and fast factory. Its memory, where all the data lives, is this huge but slow and kind of distant warehouse. So for every single tiny operation, a truck has to drive all the way to the warehouse, pick up some data, drive it back to the factory, let the factory do its work, and then drive the result all the way back. That round trip, that's where we're losing all our time.
So in this explainer, we're basically going to stage a race. We'll start by finding the bottleneck with some pro-level tools. Then we'll test the standard everyday approach, a really hardcore manual method, and finally, a couple of modern automated tools. Let's see who comes out on top.
All right, so the challenge is pretty simple. We need to implement a really common piece of a neural network, an activation function called GLU. Now, don't worry about the math, just know it's a fundamental building block. We're going to code this thing in 4 different ways and time each one. The goal? Find the absolute fastest method, and, more importantly, understand why it's the fastest.
But listen, before we even think about optimizing, we have to measure. As the experts always say, you just can't improve what you can't measure. If you just guess where the slowdown is, you can waste so much time going down a total rabbit hole. We need to use precise tools to find the real culprit.
Okay, so our 2 main tools here are benchmarking and profiling. You can think of benchmarking as our stopwatch. It just tells us the total time from start to finish. But profiling is our slow motion camera. It lets us see inside the code's execution moment by moment to find out exactly where that time is being wasted.
And, you know, there's a right way to do this. First, you always do a warm-up lap. That gets rid of any one-time setup costs. Then you have to synchronize the CPU and the GPU to make sure they're starting the clock at the exact same time. You time it a bunch of times to get a good average, and then you dive in with that slow-motion camera, the profiler.
Let's get to our first contender, what we're calling the naive PyTorch way. Now, PyTorch is this super popular library for building AI models in Python. This method is how pretty much everyone would start out. You just take the math formula and write it out, line by line. It's simple, it's easy to read, but is it fast?
The second we put this code under our profiler, our slow-motion camera, we see the problem. It's so obvious. Each little step in the math, the multiplication, the addition, all of it became its own separate operation. In our analogy, that's a separate truck driving from the warehouse to the factory and back. For every single step, it is just incredibly inefficient.
And yep, the stopwatch confirms it, a painfully slow 8.1 milliseconds. Now that might sound fast, but in the world of high-performance computing, that's an eternity. This is our baseline. We can definitely do better. Okay, time for contender number 2, the expert approach. We're going to completely bypass PyTorch and write our code directly for the GPU using C++ and a special framework called CUDA. You can think of CUDA as the native language of the GPU. It gives us total, low-level control over the hardware. It's way more complex, but it lets us do something really powerful.
And this gets right to the heart of the solution. We create what's called a fused kernel. So instead of sending a different truck for every little task, we write one single complex instruction. It tells the factory, go to the warehouse one time, grab everything you need, do all the math in one single go, and then bring the final result back. One trip. That's the whole key.
And would you look at that time, 1.8 milliseconds. That is over 4 times faster. That is the power of getting rid of all those back and forth trips to memory. This is a massive leap in performance.
But let's be real, writing low-level C++ is hard. It's time-consuming. What if there was a better way? Let's meet our final 2 contenders,
Triton and torch.compile. These are modern tools that are designed to give us the speed of CUDA, but without all the complexity.
So what's the real difference here? Well, with CUDA, you're in C++, and you literally have to micromanage every single little worker thread. It's a lot. With Triton, you get to stay in Python, and you think at a higher level. You manage blocks of threads at a time. The compiler handles all the messy details for you, which makes it so much easier and safer to work with. And the results are just wow. Our handwritten Triton kernel clocks in at 1.8 milliseconds. It exactly matches the hardcore C++ version, but we wrote it in nice, friendly Python. But here's the real kicker. Torch.compile, which is basically an auto-optimize button, it looked at our original naive code and automatically wrote an optimized Triton kernel for us. And get this, it was even faster at 1.47 milliseconds.
So, the race is over. Let's just pull back for a second and look at the final leaderboard to really see what we've learned.
I mean, the visual here just says it all. The naive approach is completely left in the dust. The hand-coded methods, CUDA and Triton, are neck and neck, but the automated compiler, torch.compile, actually pulls ahead to take the gold. The performance difference is just staggering. So here's the breakdown. Naive code? Easy, but slow. C++, CUDA? You get total control, but it's super complex. Triton gives you that same power, but with the ease of Python. And torch.compile? Well, it pretty much gives you the best of all worlds by just automating the whole process for you. So the big takeaway, the crucial point is this. Performance isn't just about how many calculations you can do. It's about being smart with your data. To make AI fast, you have to fight that memory bottleneck by minimizing how much you move data around. And fused kernels, doing all your work in a single trip, are the single most important weapon in that fight.
And that leaves us with a really fascinating question for the future, right? I mean, torch.compile actually beat our hand-tuned code. So as these automatic tools get even smarter and even better, are we heading towards a future where the whole art of writing low-level, high-performance code just becomes a thing of the past?